All right, section 2.5 is all about symmetry. And we're still talking about functions. This whole chapter has been dealing with functions in some shape or form, doing different things with those functions. Today we're going to talk about symmetry of graphs and functions. We've looked at all different kinds of graphs of these functions. And obviously, quadratic we know makes a parabola, and we know the cubic makes like the snake-like graph and the V graph and all of that. But today we're going to talk about the graph of that and if it's symmetrical. And we're going to determine the symmetry based graphically, for one, but then also how can we do it algebraically. And we'll talk about why we would need to do it algebraically if we don't necessarily know what the graph looks like. Okay. Graphically would be the easy way to go. So I'm going to show you graphically first. There's three kinds of symmetry that we're going to talk about today. There is symmetrical to the x-axis, symmetrical to the y-axis, and then symmetrical to the origin. So if a graph is symmetrical to the x-axis, then it will have the opposite y value. Okay. And if you'd rather write it out as the opposite y value, I just put a negative y value, because if it's positive, it becomes negative. Negative becomes positive. So opposite y value. Basically, all we're doing is reflecting it over the x-axis. That's what makes the symmetry, right? The x-axis is the line that is splitting it right down the middle, so we call that the line of symmetry. You've seen and heard the line of symmetry before. Kind of like our bodies are symmetrical. If you split us right down the middle, we got an arm on both sides, eyes, ears, legs. We're symmetrical, right? And so, same thing here. Splitting it right down the middle is the same on either side. All that happens is those points just get reflected to the other side. Okay, so that's what a graph symmetrical to the x-axis would look like. If a graph is symmetrical to the y-axis, it will have the opposite x value. So if I still had a point at 3, 2, now when I flip it, I'm going to flip it over the y-axis. So now it's going to be negative 3, 2. So if I go right 3 and up 2, when I flip it, now I'm going to go left 3 and up 2. So the x value is the opposite value, whichever way you flip it. You go from negative to positive, positive to negative. The y value stays the same here. The x value is the one that changes. Okay, both of those I think we've kind of seen a little bit of that before. A graph like this is not very common. Okay, we won't see something like that a whole lot, except when we're doing and talking about symmetry. We see parabolas all the time, so we see graphs that are symmetrical to the y-axis a lot more. A graph that is symmetrical to the origin is going to look like this. Okay, and I'm going to use the same point once again. I'm going to use the point 3, 2. But this time, we're going to flip it over both axes. So we're going to flip it over the x-axis, and we're going to flip it over the y-axis. And it's going to end up in the opposite corner that we started with. So it's going to have the opposite x value and the opposite y value. It's going to have both of those. So this point down here would be -3, -2. So it's symmetrical through the origin because it basically reflects over that origin. But I think the easiest way to think about it is it's reflecting over both axes, which makes it reflect through the origin. Okay, so that's what we're doing if we're doing it graphically. And that's why I feel like graphically is easy to tell, right? If I look at a graph, then I can just look at that graph and say, is the x-axis splitting it in half? Is the y-axis splitting it in half? Or is it symmetrical to the origin? And we're going to see all kinds of different graphs today, which is going to make it a little bit harder to determine. But then we're going to see some that we can't necessarily graph. Okay, so I'm going to give you an easier example. Instead of giving us the graph itself, they're just going to give us an equation or a function. And then the question is going to be, is this symmetrical to the x-axis, the y-axis, or the origin? Okay, which one of those three? And here's what I'll say is that it could be all three. There are some graphs that could be symmetrical to all three. There's obviously some graphs that are only symmetric to the x-axis, only to the y-axis, or only to the origin. Or in some cases, you might say none of those, right? It may not be symmetrical to any of those. So you have all kinds of options that it could be based on what it looks like. Now, if I were to graph this, okay, then this would be a whole lot easier problem. Because if I graph this, the function itself, let's just do it over here, is going to look like this. It's going to go up to, and you could put it into your calculator and look at the graph. And if I had to determine what kind of symmetry is taking place here, what would we say? The y-axis, okay? This is symmetrical to the y-axis because the y-axis is the axis that splits it down the middle, okay? And for me, that would be the easiest way to go. But I'm going to show you how we can do this algebraically. And then I'll show you an example here in just a second where kind of shows you why we have to do it algebraically. For this one, we wouldn't necessarily have to do it algebraically because the easiest way it would be to graph it and just look at it and determine what kind of symmetry is taking place. Okay, so we're going to make 3 columns. We're going to do a little bit of work algebraically for the x-axis, the y-axis, and the origin. Okay? The x-axis, like we just talked about, is going to be the opposite of y. Okay? The y value will be the opposite if it's symmetrical to the x-axis. And so what that means is we're going to take the original equation, and we're going to put negative y in place of y. And then I'm going to solve that equation for y. I'm going to get y by itself, just like I typically would do. Well, the only thing I can do here is get rid of the negative, so I got to divide everything by a -1. And then the question that we're going to ask ourselves, is this the same as the original? Is this equation and this equation the same? No, right? Because now we have negatives in here instead of positives. Okay, and so if it's not the same, then it is not symmetrical to the x-axis. So we just write a simple no. We're trying to figure out what type of symmetry do we have going on here. Okay, then for the y-axis. The y-axis, we're always going to use the opposite of x. So we're going to put negative x in place of the x. So we have y equals x squared plus 2. And this negative x right here is going to go in where the x is. Okay, and now here's a really important thing. Notice how I put the negative x in parentheses, and we've talked about that from time to time. When I put that negative x in parentheses, it's really important because when I square a negative, it's going to become positive, right? If I don't put that in parentheses, then I may not see or know that that's really going to become a positive. A negative and a negative would make this a positive, which gets us back to the same equation. This is what we end up with. It's the same as the exact same thing we started with. And so here we would say, yes, this is symmetrical to the y-axis. If I'm going to do the origin, and we're always going to check all three, we're going to do the opposite of x and the opposite of y. We're going to do both. So in this case, we're going to put a negative y in place of y. We're going to put a negative x in place of the x. And then we're just going to simplify it. And our goal here is to get y by itself and see if it looks exactly like the equation that we started with. Well, we're going to square it first. And then we're going to divide by negative 1. And what I get here should be the same as what I start if it's symmetrical. And it's not, so we would say no. This is not the same equation, so it's not symmetrical. Hey, so it was kind of a long process, right? We do all of this work and we get to the result that yes, it is symmetrical to the y-axis, where it was much easier just to say, hey, we graphed it and we came up with the same result, right? So then you might be like, well, why do I go through all of that work to get to the same thing I can do if I can graph it, right? What if we have a function that we don't know what the graph looks like? And that's where we have an issue, okay? If I know what the graph looks like and I can put it into my calculator, then graphing is the way to go, 100%. So much quicker, so much easier. All you have to do is ask yourself which axis or what's happening, what is the symmetry that's taking place, okay? We don't have to necessarily go through all that work. Then that means that it was symmetrical to the y-axis, therefore it would be even, okay? So that's the first thing. Okay, but if I gave you an equation that looked like this, kind of a weird looking equation, right? We've never seen anything like this before. First question, can I put this into my calculator? No, because what is it? What would we have to do to put this in my calculator? Get y by itself. Is this going to be really easy to get y by itself? No, not with all those exponents there, right? So it's going to be really hard to get y by itself. Anybody know what this graph's going to look like without graphing it? Probably not, right? We've never done one like this before. So it's kind of hard to know what it's going to look like if we've never done that before. And so that makes this difficult to do. So I can't just graph it and say, boom, I already know what the symmetry is going to be. So here's where algebraic is going to come into play. Okay? And here's where we would actually use the algebra to get where we would need to be. And so we're going to go through the same process as we did just a second ago. We're going to do x-axis, y-axis, and the origin. And we're going to basically go through the whole thing again. We're just using a different equation. Okay? For the x-axis, we always use the opposite of y. So we put in the opposite of y in place of y. Okay, and we talked about this just a second ago. When we square something, we know it makes a positive. What happens when we take something and raise it to the fourth power? It's still positive, right? Any even exponent will always make that back positive. Okay, so if the exponent's 2, 4, 6, whatever. If my exponent was odd, 3, 5, or 1, or something like that, then it's going to make it negative. Okay, so in this case, raising a negative y to the fourth power is going to get it back to positive again. And we get back to the original equation. So this would be, yes, symmetrical to the x-axis. But we can't just stop there, okay? Because what we talked about before is sometimes it's symmetrical to 2 of the 3, sometimes it's symmetrical to all 3. There could be a lot of different options here. So we got to check all 3, even if we answer yes or no on the first one. Okay, for x-axis, we're going to do the opposite, or for the y-axis, sorry, we're going to do the opposite of x. That goes in for x. And once again, if I take a negative and raise it to the second power or square it, it's going to make a positive, okay? So this becomes x squared plus y to the fourth equals 5, which is the same equation that we started with again. So that is also yes. And if we do the origin, we're going to do the opposite of both, x and y. So we're going to do negative x squared plus negative y to the fourth equals 5. And when I square the negative x, it makes a positive. When I take negative y to the fourth, it makes it positive. And so we would say yes for all 3. This graph is symmetrical to all 3 of those. What would that look like? Anybody have an idea? A spider. It's interesting. Maybe, I guess. If the spider is centrally located on the... I've never graphed a spider before. What kind of shape might we see that would be symmetrical to all 3? What'd you say? Circle. Yeah. That's why we would need to do something algebraically, right? We can't graph it. We don't know what it looks like. If they give us a weird function or that function is difficult to solve for y, we may not be able to put it into our calculators. But otherwise, if we can, then once again, our calculator is a great tool. And if we can plug it in, then by all means, we should be able to do that. Symmetrical to the x-axis because, or symmetrical to the y-axis, because when I say something is symmetrical to the y-axis, all I did was plug a negative x in, right? I plug negative x in place of x, and then I determine if it's the exact same thing. And if that was the case, okay, the other thing that we are going to talk about today, the other main topic, is a function even versus odd, okay? So once again, they're going to give us an even, or they're going to give us a function, and we have to determine is that function even, odd, or in some cases we may say neither, okay? It may be neither one of those. Kind of like symmetry could be none of the above, okay? It might not be symmetrical to anything. Okay, if a function is even, then a key is that it is also symmetrical to the y-axis. The graph would have to be symmetrical to the y-axis. So that's how you could do it graphically. If I can look at the graph, if the graph is symmetrical to the y-axis, then I would say, boom, it's even. Like for instance, this one right here. I see that this one is symmetrical to the y-axis, so in turn I would say that this is an even function, okay? And so that's a quick and easy way to do it graphically, but with this one we're also going to do it algebraically. And you're probably going to be a little bit lost when I write this up here, but I'll explain it to you. If I plug a negative x into a function and I get back to the original, then it is an even function. Well, that right there is the definition of an even function. Or if it's an odd function, it will be symmetrical to the origin. Okay, once again, when I write this little rule up here, you might be kind of wondering what the heck's going on here, but I'll show you an example of how we can do it. Okay, so I'm going to give you a couple of examples of how we're going to determine even versus odd. Okay, and we're going to do them algebraically, and we're going to plug in some things, and we're going to determine what type of function we have. Not just the symmetry, but if it's even versus odd. And if it's neither one of these, if I try the even and then I try the odd, and I say no on both of those, then my result would be that it's not even or odd. So it would be something we call neither even or odd. Okay, let's start with this. I'll go back to what we said for an odd function. F of negative x equals negative f of x. Okay, so here, guess what? We've already done this. We've already done the left-hand side. We already plugged a negative x in, right? We got to do this side first. We have this equation, function, and the first thing that we're always going to try is even. We're going to see if this function is even. And if it's not, then we'll try odd, and then if it's no on both of those, we'll say neither. In order for this to be even, f of x has to equal f of negative x. In this case, because we have an h, just to make it more sense to what we're doing, this is what I wrote up just a second ago, but now because my function is written as h of x, I'm just trying to show you that it really doesn't matter if it's f or h or g or whatever letter they use. Don't let that confuse you. It's the same idea. It's just a function. It's just terminology that we use for that function. So that means the original function, h of x, has to be the same as if I plug a negative x in to this function, okay? So I don't really need to write anything here. This is the function that we started with, right? So now what I'm going to do is I'm going to plug negative x in place of all my x's. And it looks like it's really difficult, right? And it's not a whole lot different than what we were doing earlier, because all that's happening here is we're plugging in a negative x, and you think, oh man, there's all kinds of algebra going on here. All you really have to do is pay attention to your exponents. If my exponent is even, what's going to happen with this negative right here? It's just going to become positive, right? And so this becomes 5x to the 6th. And then once again, I got another even exponent, so when I take negative x and square it, once again, makes it positive. It doesn't make the 3 positive, right? Only what's inside the parentheses. So this is still a negative 3x squared minus 7. Is this function the same as what I started with? Yeah, okay? So if these two are the same, h of x and h of negative x are the same, then we would say that this is even. This is an even function. And we're done, okay? Because we're not, in this case, it's either going to be even or odd, okay? We're not talking about symmetry here. We're talking about even versus odd function. All right, let's do one more. Okay, let's start with even. Okay, I want h of x to equal h of negative x. So we're going to put a negative x in every place that we have an x. We got 3 places. 5, and the most important thing here, more than anything else, is just your signs, right? The signs, positive, negative, that kind of thing. Because I'm raising a negative to an odd power, what's that going to do to my sign? Negative to the 7th power. Stays negative, you bet. Okay? So that's going to make this negative 5x to the 7th. I'm just going to put that negative in front of the 5 because we're taking 5 times negative x to the 7th. Okay? Same thing here. Negative x raised to the 3rd becomes negative x, right? Negative 6x times negative makes this a positive 6x cubed. And then finally, negative 2x times negative x would be a positive 2x. Is this function the same as what we started with? No, all the signs are different, right? It's close, but once again, the signs are the thing that are changing. That's why we got to be really careful with the signs. Okay, so here we're going to say no. This is not an even function. That doesn't automatically mean that it's odd. So if you say no to even, that doesn't mean, oh, it must be an odd function then. Because remember, it could be neither. So then what we have to check is this an odd function? Okay, now this is the one we haven't done yet. What we're going to do here, so here's what this one's going to look like. I'm going to write up h of negative x has to equal negative h of x. This goes right here, okay? So do we need to do it again? Not unless you really want to, right? I don't want to do it again, okay? We've already done it, so you've already got that result. So now all we got to do is really check this part, okay? Negative h of x. And this one's not that big a deal, because all we're doing is putting a negative in front of the original function. Here's my original function. We're putting a negative in front of it, okay? So here's all we're doing. We put a negative in front of the entire function. I put it in parentheses. What am I going to do with that negative that's out in front? It's distributed, right? And so all that's going to do, once again, is change my signs. Are these two exactly the same thing? Yeah, okay. If those two are exactly the same, that means they're equal. So that means this would be an odd function. If I say no here, then we would say neither. Okay. So when you write out the terminology, it kind of looks confusing, but when you kind of break it down and understand what's going on, it's not as bad as what it originally looks like, I don't think. At least I hope not. Okay, assignment for today. Could be a circle or it could be an ellipse. I know that you guys don't really know what an ellipse is right now, but it could be a circle, right? The x-axis is splitting it in half, the y-axis is splitting it in half, and then I could take this point and reflect it over here, and it would be symmetrical to all three. As long as it's centrally located on the x and y-axis, then we could do that. If it's like shifted over, then it may not be to all three. Okay. So, and that's not something that we would typically graph on our graphing calculators. When we do circles later on in the semester, if we get to it, then we'll talk about ways that we can graph it. You might remember that from geometry a little bit, where we graphed a little bit of circles on a coordinate plane. And so it's a little bit different equation. We talked about the equation early on in chapter 1, and we did a little bit of graphing of it, but we didn't necessarily talk about symmetry and those kind of things. Okay, so